Hello everyone, welcome to the intro to some basic probability. We're going to cover the bullet points below with a bunch of different examples. So let's go ahead and get started with the definition of theoretical probability. It's the number of possibilities that meet a condition divided by the number of equally likely possibilities. Let's go ahead and get started with our first problem here. It says that a die is rolled once. Find the probability of getting a number less than 5. So a die has 6 sides to it, and the sides range from 1 through 6, and we're looking at numbers less than 5, so that means we're looking at 1 through 4. And so we have 4 different possibilities that are less than 5 out of a total of 6 sides, which means if we reduce, we have a 2/3 chance of getting a number less than 5. Two ordinary 6-sided dice are rolled. What is the probability of getting a sum of 8? So here we have our different possibilities of different sums when we roll 2 dice, a first die and second die. And we have a total of 36 different outcomes. And right here we have the sum of 8. And if you count them out, we have 1, 2, 3, 4, 5 different ways that we can sum to 8. So we have a 5 out of 36 chance of getting a sum of 8. Let's move to the next one. When flipping 3 coins, find the probability of getting exactly 2 tails. So I'm going to start off by writing out all my possibilities here. And how many possibilities could we have? Okay, we're flipping a coin 3 times, and each time you flip a coin you have either heads or tails. So we have 2 different possibilities, and we have 2 different possibilities in the second flip, and then 2 different possibilities on the third flip. And so the number of different outcomes that we could see here would be, if we multiplied the 2's, we end up with 8 different possibilities. So here I've listed all of the different possibilities that we could get when we're flipping 3 coins. And we want to find the probability of getting exactly 2 tails. Exactly 2 tails. Does not mean 3 tails. We're talking about exactly 2. So this is one option. Tails, heads, tails. And then here's another option with tails, tails, heads. And then our last one right here is heads, tails, tails. And that means that we have a 3 out of 8 chance of getting exactly 2 tails. We're going to look at OR probabilities with mutually exclusive events. It says if A and B are mutually exclusive events, then the probability of A or B occurring is found by adding the probability of A plus the probability of B. Let's work on a problem with mutually exclusive events. If one card is randomly selected from a deck of cards, what is the probability of selecting a king or queen? Well, first of all, we have a standard deck of cards which has 52 cards in it, and we have 4 queens within that deck, and we have 4 kings within that deck. And independently, the probability of selecting a queen is a 4 out of 52 chance. And also the king has a 4 out of 52 chance independently of being selected. If you want to figure out king or queen, you simply add these 2 probabilities together and end up with an 8 out of 52 chance, which then will reduce to 2 out of 13. Okay, another one here. If you roll a single 6-sided die, what is the probability of getting either a 4 or a 5? Well, the probability of getting a 4 is just a 1 out of 6 chance, and the probability of getting a 5 is also just a 1 out of 6 chance. So if you add these two probabilities together, you end up with a 2 out of 6 chance, which represents 1/3. You have a 1/3 chance of getting a 4 or a 5. Okay. Vin Diamond wants to book a weekend of dates. He has a 50% chance of getting Roach Coach and a 25% chance of getting Jarvis Parvis to go out with him this weekend. If he asks both girls, what is the chance of going out with Roach Coach or Jarvis Parvis this weekend? Well, this just represents adding 25% to 50%, which means that Mr. Diamond has a 75% chance of hooking up a date this weekend. We're going to look at OR probabilities with events that are not mutually exclusive. So here we have, if A and B are not mutually exclusive events, then we find the probability of A or B occurring by adding the probability of A to the probability of B, and then subtracting the probability of A and B both occurring. Let's go ahead and see this within the context of a problem. I believe it makes a lot more sense this way. Here we have to consider a standard deck of 52 cards. Suppose that these cards are shuffled and you randomly select one card from the deck. What is the probability of selecting a diamond or a picture card? So we first want to figure out the probability of selecting a diamond, and then the picture card, and then figure out the probability of the diamond picture card. So let's start off with the diamond. There are 13 diamonds out of a total of 52 cards. So we need to add that on to the picture cards. Okay, so picture cards are the Jack, King, Queens. And if we go through each suit, we have a total of 12 of them. So we have 12 out of 52. And so our problem here is that we're double counting. We're double counting these cards here. We already counted the diamond cards, and now we're double counting the picture cards. And so we need to subtract the diamond picture cards. Okay, so we're subtracting 3 out of the 52. And so if we combine all together, we end up with a 22 out of 52, which then would reduce to 11 out of 26. And here we have a good visual of what just occurred. We have a Venn diagram, and we have the 13 out of 52, and we have the 12 out of 52, and then here at the intersection of the two, we have the 3 out of 52. If you count out all of these together, we have 22 out of 52. Let's try this out again. We have, if spun, it is probable that the pointer down below here will land on any one of the 8 regions, numbered 1 through 8. Find the probability that the pointer will stop on an even number or on a number greater than 5. So let's figure out the probability of an even number. We have a total of 4 out of 8 even numbers from 1 through 8. Now let's figure out the numbers greater than 5. The numbers greater than 5 are 6, 7, 8, and so that represents a 3 out of 8 chance of getting a number greater than 5. Now we don't want to overcount, so we need to figure out the even numbers that are greater than 5, which are the 6 and the 8. So that represents a 2 out of 8 chance. So we have to add the even numbers, the probability of selecting an even number, to the probability of selecting a number greater than 5, and then subtract the even numbers greater than 5. And this means that we have the probability of 5 out of 8 getting a even number or a number greater than 5. Let's look at the Venn diagram to get a visual of what's going on. Here we have our even numbers. Here we have our numbers greater than 5. And right in the middle, we have the even numbers that are greater than 5. And count all these numbers, and we have a 5 out of 8 chance of getting them. Okay. A group of people is comprised of 15 U.S. men, 20 U.S. women, 10 Canadian men, and 5 Canadian women. If a person is selected at random from the group, find the probability that the selected person is a Canadian or a man. Let's figure out the probability of selecting a Canadian. We have a total of 15 plus 20 plus 10 plus 5 people there, so that's 50 people. And we have 10 plus 5 Canadians, so that's a 15 out of 50 chance of selecting a Canadian. We're going to add that to the probability of selecting a man. There are a total of 15 plus 10 men, so that's 25 out of 50 chance of getting just a man. And then we need to subtract the Canadian men because we don't want to double count. So we're going to subtract 10 out of 50. And that is going to give us, let's see, 30 out of 50, which will simplify to 3/5. We have a 3/5 chance of selecting a Canadian or a man. Now we're going to look at AND probabilities with independent events. If A and B are independent events, then the probability of A and B both occurring is found by multiplying the probability of A times the probability of B. Our first problem here, we have Mr. Fulton Bolton wants to book a weekend of dates. He has a 50% chance of getting Miss Meeky Beaky and a 25% chance of getting Miss Nielsen Quilson, and a 0% chance of getting Miss Transtan to go out with him this weekend. If he asks the eligible ladies what is the chance of going out with Meeky Beaky and Nielsen Quilson this weekend, this is an AND scenario. So we're going to have to multiply the probabilities of getting a date with Meeky Beaky and Nielsen Quilson. So let's see. So the 1/2 represents 50%, and the 25% is represented by 1/4. If we multiply 1/2 times 1/4, we end up with Mr. Fulton Bolton having a 1/8 chance of getting both dates for the weekend. Now I'd like to look at this visually as well. This red bar here represents 100% chance. Okay, so let's look at first 50% chance. So, all right, so if this is 100, well, 50% is right here. 50% is right here. So then, of that 50% chance, Mr. Fulton Bolton has a 25% chance of getting Nielsen Quilson. So I'm going to go within the 50% and section off fourths to find right here. This is 25%. And 25% of 50% represents 1/8. And you would more clearly see that if I were to show you all of these intervals all the way down to 100%. So this is his chance here, which does represent a 1 out of 8 chance of securing both dates for the weekend. Okay, so for our next problem, we have on a multiple choice test, problem 1 has 4 possible answers and problem 2 has 3 possible answers. There is only one correct answer. What is the probability of randomly guessing the correct answer to both problems? So what I have here is a matrix with problem 1 and problem 2. In problem 1, let's say we have A, B, C, D as possible answers, and E, F, G as possible answers for problem 2. And let's say that the correct answer for problem 1 is B and the correct answer for problem 2 is G. Well, there's only one way that we can get both of these right, and that's by selecting B and G. Well, if we count out all the cells possible, there's 12 cells, and that means that we have a 1/12th chance of getting that correct answer. Another way of looking at this is if we take the probability of selecting the answer from problem 1, that's a 1/4 chance, and the probability of selecting the correct answer from problem 2 is a 1/3 chance. And then if we multiply those two probabilities together, then we have a 1/12th chance of getting it correct. That's, of course, if we're just randomly guessing. So this next one, we have using a 6-sided die numbered 1 to 6, find the probability of rolling odd numbers 3 times. Well, on a 6-sided die, we have 3 odd numbers, 1, 3, and 5. So we have a 3 out of 6 chance of getting an odd number, which then will reduce to 1/2. So if we multiply 1/2 times 1/2 times 1/2, we end up with a 1/8 chance of rolling odd numbers 3 times. So that's just like Mr. Fulton Bolton, huh? Okay, so a family has had 9 girls in a row. Find the probability of this occurrence. Well, when you have a child, you have a 1/2 chance of having a boy or a girl. And so we would need to multiply 1/2 a total of 9 times. So our probability is just going to be 1/2 to the 9th power, which I believe is 1/512. Hopefully I didn't make a mistake there, but I'm just going to jam to the next one here. We're going to look at dependent events now. We're moving away from independent events. And we have a bag that contains different colored marbles, 3 blue, 2 red, 4 green, and 1 yellow. A marble is chosen at random. Then without replacing it, a second one is chosen at random. Find the probability of pulling a blue marble and then a green marble from the bag. So let's go ahead and start off by finding the probability of pulling a blue marble from the bag first. We have 3 plus 2 plus 4 plus 1 marbles. That means we have a total of 10, and so pulling a blue at first represents a 3 out of 10 chance. Now, we want to pull a green one after that. And the reason why this is a dependent problem is because once we've pulled the blue, there's 1 less marble. And so now we have only 9 marbles in the bag. And so we have there's 4 green, so we have a 4 out of 9 chance then of getting a green. And if we multiply these two probabilities together, then we have a 12 out of 90 chance there. And 12 out of 90 then will reduce to 6 out of 45. And, we could reduce that more, right? So we have a 2 out of 15 chance there. All right, let's look at another dependent problem. We have a card is chosen at random from a standard deck of 52 playing cards. Without replacing it, a second card is chosen. What is the probability that the first card chosen is a queen and the second card chosen is a jack? So recall from the previous problems that there are 4 queens within a 52 standard deck of 52 cards, and there's also 4 jacks within a standard deck of 52 cards. So we first have a 4 out of 52 chance of selecting a queen. Now once we've picked that queen, now we only have 51 cards. we still have the 4 jacks. We have a 4 out of 51 chance of getting that jack. And so we have to multiply these two together and simplify. Let's see. What we get is a 4 out of 663 chance. Alright, let's move on. We're going to look at probability with permutation here. Oregon's lottery game Lotto Mucho is set up so that each player chooses 4 numbers 1 to 20. If the 4 numbers chosen exactly match the 4 numbers in the same order, the player wins the top cash prize. With one Lotto Mucho ticket, what is the probability of winning this prize? So we have 4 numbers to choose here from 1 to 20. And the first number that we pick, we have 20 different options, but once we pick that first number, we only have 19 options, and then 18, and then 17 options. So to figure out the total amount of options possible, we have to multiply these together. And we end up getting 116,280. So the probability of actually winning this prize represents a 1 out of 116,280. So just remember that the order matters means that if the winning numbers come out as 3, 20, 17, and 14, we have to exactly match that order with the 3 first, then the 20, and then the 17, and then the 14. That's a permutation. A combination, remember, is when the order doesn't matter. So if this represented a combination problem, we could have picked the 14 first, and then the 3, and then the 20, and then the 17. As long as we get those same numbers, then we would win if this were a combination problem. And why do I bring up combination? Because that's the next problem here. We have Florida's lottery game, Lotto Max, is set up so that each player chooses 6 numbers, 1 to 53. If the 6 numbers chosen match the 6 numbers, the player wins the top cash prize. With one Lotto Max ticket, what is the probability of winning this prize? So let's figure out how many different combinations we have. And remember, it's easiest to find a combination by first looking at a permutation. So we have 6 numbers to choose from. And we have 53 numbers actually, but we have 6 spaces available. In the first space we have 53 numbers, and then the second we have 52, and then 51, 50, and 49, and then 48. And so if this were a permutation, we would simply just multiply all these numbers together. But this is not a permutation. Order does not matter in this case. And so what we need to do is we need to divide by the number of ways in which we can arrange those 6 numbers. And that means that we're going to have to divide by 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. And I said 3, but I didn't write it. Okay, so we end up with 22,957,480. And our chances of actually winning the prize represent a 1 out of 22,957,480. So remember, if this were a permutation problem, we would have even less of a chance of winning. Alright, let's move on to the next problem. We have probability of an event not occurring here. The probability that an event E will not occur is equal to 1 minus the probability that it actually will occur. So this one piggybacks off of the previous problem we did with a combination. We have seen that the probability of winning Florida's Lotto with one ticket is 1 out of 22,957,480. What is the probability of not winning? Well, we would simply need to subtract the probability from 1, the probability of winning from 1, and that gives us, I'll go ahead and pause it for you. Okay, so there's our probability of actually not winning, right? And let me show you the actual decimal, which converts to 99.9999999 Not very likely. Okay, so here I have a problem pretty much done for us. When flipping 3 coins, find the probability of getting at least one head. Well, this is kind of piggybacking off one of the problems we did earlier. Remember flipping 3 coins, we have 2 options, 2 options, 2 options, right? And so there's a total of 8 possibilities. And if we want to figure out the probability of at least one head, well, we have to think about the probability of just getting all tails, because there's no heads with all tails. And the probability of tails, tails, tails is just a 1 out of 8 chance. And so we have to say 1 minus 1 out of 8, and then that would give us the 7 out of 8 chance of at least getting one head. Okay, so I will see you all in class. Hopefully this is enough so that you can get your start with the project.